The Levitating Balloons Experiment by Cameron, Pedro, and Jay. Our experiment's purpose was to determine the charge given to a pair of balloons. Our hypothesis was that due to the likeness of the charges on the balloons, they would repel each other and the free-moving balloon will remain horizontal when the force of repulsion is equal to the force of gravity. The punchline for the experiment was to find the magnitude of the charges on each balloon by setting the electric force equal to the gravitational force when at equilibrium and acceleration is 0, so net force is 0. Our main findings were that the balloons repulsed each other, and the point of equilibrium for the free balloon was found to be an average of 0.033 meters, which we used to find the magnitude of the charges on the balloons. Our experimental design included charging each balloon the same exact way, and the bottom balloon was fixed, and the top balloon was held in our hands by the balloon knot, and to determine the point at which the gravitational force and electric force was equal, we moved the balloon up and down till we found the point where we assumed that the acceleration was 0, and that's when the balloon was horizontal, so the gravitational force and electric forces were equal on the balloon. And once the equilibrium point was reached, we measured it with a ruler, and we conducted 3 trials to determine the average. And another assumption that we made during this experiment was that the balloons were both positively charged.
Here we have the models for the experiment. So we have these force diagrams of balloon 1 and balloon 2 as depicted on the previous page, red and blue. We have the equilibrium when the balloon is tilted farther down or when the balloon is tilted up of the balloon 1. And so we took the value of the distance at this equilibrium where the force electric of the balloon 2 onto balloon 1 was equal to the force gravity of the ground onto balloon 1.
This is when the force gravity and force
When it's tilted
electrical
down or
are
tilted
the
up,
same
that means there's
magnitude.
more force gravity or force electric being pushed on the balloon, and it is not equal to each other. For the bottom balloon, when the top is at equilibrium, we have the force normal being pushed up onto that balloon, which is going to be equal to the combination of the force gravity and the force electric. Coulomb's laws tells us that our charges are the same since the balloons are repelling, and that repulsion is the electric force in action. For the data, we collected that distance and the mass of the balloon, so we collected it in centimeters and converted it into meters to use it in the equation, with the average distance being 0.033 meters, and the mass of the balloon on a scale using 0.0032 kilograms. We plug it into the equation using force of gravity equals mass times the gravitational constant, and we're assuming that acceleration is 0 because when we were at that equilibrium, when there was no movement of the balloon, it wasn't moving up and down, it was actually at a constant level. And so that's going to be the mass times 9.81 meters over second squared to get that force, 0.0314 newtons. We can set that equal to the force electrical equation with Q being squared because both charges are the same. And we can calculate that Q is 6.167 e to the negative 8th coulombs.
We found the charge to be 6.17 times 10 to the negative 8 coulombs on one balloon, and we know the charge of the electron is negative 1.602 times 10 to the negative 19 coulombs. So doing the math, we found that the number of electrons transferred during the charge was about 3.850 times 10 to the 11th electrons. Since we made the assumption that the balloons are both positively charged, this means that the electrons are transferred from the balloons to the ground while charging them. Using our design, we were able to see changes in the free balloon's tilt, which helped us model the interactions between it and the fixed charge balloon, as well as with the Earth. Assuming that both balloons had the same positive charge, since they were charged in the same manner, we determined the charge to be 6.17 times 10 to the negative 8 coulombs, which means that we had 3.85 times 10 to the 11th electrons transferred away from the balloon. So some potential errors include the charge of the balloon is not being concentrated where we thought it was, the mechanism for the top free moving balloon having error for not being too precise, the difficulty in determining the equilibrium and matching the ruler with the balloons to measure as precisely as possible. Another limitation can include the smallest possible distance measurable and the ruler being millimeters, but we are very confident in the precision of our measurements since all 3 trials had very similar distances, with the change being about 0.2 centimeters for each trial. We can make a more precise measurement if we had a more controlled way of separating the balloons instead of just holding them with our hands.